Hi and welcome to Unit 1 Topic 2 Video 10, and in this video we're going to look at Applications 2, the equilibrium of forces. Learning goals there, success criteria there as usual. Feel free to pause and have a quick read. Okay, so let's have a talk about forces. A force is made up of mass and acceleration. So you might recognise the old F equals ma from physics, and that's one of Newton's laws. Force is mass times acceleration. Force is recorded in newtons, which is kilogram meters per second squared, and you can see the mass and the acceleration components of those units. Remember, a lot of these equations, the units give away what the equation is. It's a mass times a distance divided by time squared, and that is mass times acceleration. So we know that mass is a scalar. It's an important note there. It's got no direction. Mass is just a weight, and of course we use the word mass to define the mass based on gravity, but there's no direction. And acceleration is a vector. So our acceleration is it's an accelerating component of force, but it happens in a direction. So that makes it a vector. So a force is a scalar times a vector, which is a vector. A force is a vector. So here we go. Let's talk about some types of forces that you might run into. The first one is weight. So if mass is a scalar, and at the moment it's arbitrarily based on Earth's gravity, weight is a vector, it's a force, and we use weight. So a lot of people will just say this is how much they weigh and this is their weight, which is fine. It's a very common English usage, but technically in the physics world and in this dynamics-based level of maths, we talk about weight as a particular type of force, and that's the force due to gravity. So we say weight is ma. So commonly we're talking about Earth's gravity, but we might be somewhere else. My mass is a constant on Earth, unless I eat too much, and the moon, but my weight varies as gravity varies. Then we have our normal reactive force. So, and this one's really important because it's a force you don't see or probably recognise exists, but you do feel it. So normal reactive force is the force of opposing basically anything that your weight, what your weight is doing or what any weight is doing. So if you put a weight on a table. So you're currently standing somewhere or maybe sitting on a chair. So if you're sitting on a chair, then you're pushing on the chair because you're being drawn to the centre of the earth due to gravity. But that means the chair is pushing against you as well. And if there was nothing pushing against you, you would just start to travel towards the centre of the earth. So that is applying a force, and that force is called the normal reactive force, and it's perpendicular to the plane that's being applied to. So if you lean forward in your chair now, well, the force is still pushing up. Now, that's the normal reactive, we'll see that. Then we have a tension force. So you might have a tension force acting on an object. That'll be a force by a piece of elastic or a string or a rope or something like that. So I'm pulling a rope, there's tension in the rope, and it's that tension that's pulling on the object. So that's a tension force, and that's important because then you get the normal force to that tension as well, which we'll see. And then of course we have friction. Now friction's not in Unit 1, it will come up in Unit 3, and so we might talk about it a bit, but it's not covered in the particular textbook that we use, so I won't talk on it too much. So here's a question: I push on the block but it does not move. Why? And the reason is because there's friction, surface friction between the base of the block and the floor, whatever the floor is. So if I'm trying to push that block on ice, there's less friction. Ice is a easy surface to move things on because it doesn't have much surface friction. It has a low coefficient of friction, in fact, which we'll talk about later. But if I'm trying to push that on gravel or carpet, there's different levels of friction happening. Okay, now let's talk about force diagrams. So here's a force diagram, and typically we have an object in the middle here, and it's being acted on by a series of forces. Now in this case I've denoted 3 forces. One force is acting, and we could set our vectors up in the I and J components here. One force is acting entirely on the I component, that's the F1 force, and then we have force 2 and force 3 that are acting partially I, partially J. Now, there's a few things to keep in mind here. Firstly, we don't know much about this system, but those 3 forces will give us a resultant force, an overall force. And we've got two forces pulling forward, so maybe there's an overall I component, and this force 3 looks like it's pulling down a little bit more. Maybe there's an overall force pulling down and forward, and so our resultant force, RF, sometimes called N, sometimes it's called R, that resultant force is pulling here. And then we might have forces in equilibrium. So if the forces, the three of them combined means the object don't move, that means that they're cancelling each other out, and we have forces in equilibrium. So here's one thing we can do. We can combine our forces head to tail like we would with vectors, because they're all currently on 1 point. So F2 was this one. I've just taken it over here and I've moved it to there, so it's at the head of F1. And then F3 was this one. I've just taken it here and put it from starting at the head of F2, and then we end here. We started there, so the orange bit is our resultant force. This is the vector force that will result. If the 3 or more, or 2 forces finish where they started, then the forces are resolved and the object won't move. So there'll be no force, overall force on the object, which means that the acceleration is 0, because the mass is scalar, so the mass is set and it's not 0, so that means the acceleration must be 0 if there's no resultant force, and therefore if there's no acceleration and the object's not already moving, it won't start to move. So there's an example of a force diagram that would be resolved. Okay, so that's my brief summary of the types of forces we'll deal with and force diagrams. In our next video, as you can see here, we're going to start talking about examples. All the best.